of f with respect to the coordinate that you are differentiating with is not equal to 0, and this is the derivative of the implicit function. Get partial f partial x by partial f partial y. This slide, actually it's a repetition of the slides that we had previously. Suppose x and y are related to the equation, x plus cosine y equal 1. Determine dy by dx. So all I have to do, Ms. Seda, trying to get partial. First of all, let's substitute. X, I will put here x equal to 1. Okay? And for y equal to pi over 2. So cosine pi over 2 is equal to 0. 1 is equal to 1. So, which means your function is equal to 0. So, if you bring it to one side, it's going to equal to 0. مش معايا بالسيرة. The first step here in to find the solution of implicit functions is to get f of x and y equal to 0. So I will put this function as x plus cosine y minus 1 equal to 0. Now I will check that the value of f, of this function of f, at those values equal to 0. It's very easy to check. Replace x by 1, y by pi over 2, minus 1, the result is equal to 0. معايا بالسيرة? That's the first check. The second check, differentiate this function with respect to y. So partial f, partial y, it's gonna be minus sine over y. Am I right? Okay, negative sine of y, start substituting by pi over 2. The value is gonna equal to negative 1, which means it doesn't equal to 0. Now I can find dy by dx, which is gonna be partial f, partial x, partial f, partial y with a negative sign. That's what's the implicit function is telling us. Okay, so it's a direct substitution in order to get this value. Okay, once more. Those are the steps. Define the function, compute partial derivatives, plug into the formula and substitute. The first thing, this is dy by dx, that's the relation that I'm going to use. That's the function equal to 0. If you substitute by the values 1 and pi over 2, it will be equal to 0, which is correct. This is partial f partial x, partial f partial y. So dy by dx, it's going to be dividing 1 on negative sign of y, as you can see. Then I will substitute at by x and y, which is 1 and pi over 2, and so dy by dx is equal to 1 at this point. Okay, direct substitution. Okay, done. Here he wants you to check the following equations. Define locally y as a function of x at the point b node. Indicated, calculate the derivative of this function exactly like what we did. This is the first function. So I will take 1 and 1. Let's substitute together. This is going to be positive 1. Am I right? And this is going to be positive 3. 1 plus 3 is equal to 4. Minus 4, the result is 0. That's the first check. The second check. Get the partial derivative with respect to y. Differentiate with respect to y. Which is going to be x squared. And then going to be 9y squared x to the power of 4. Substitute at 1 and 1. It's not equal to 0. So I can get the relation. What's the relation? How to get the derivative? Let's see that dy by dx is equal to negative f sub x by f sub y. So I will get the derivative f of x, get the derivative f of y, divide them on each other, then substitute by the point. It's a direct relationship. And all of this has been explained in this lecture at the beginning of this lecture today. So once more, those are the steps. I've tried as much as possible to solve plenty of problems, and on each problem repeat the sequence. Okay. So once more, this is the f function. This is f sub x, f sub y, as you can see. This is the value at 1 and 1, and this is f of y. As you can see, it's still not equal to 0, so the conditions is okay. Divide them on each other. That's the value of the implicit function at the point 1 and 1. Here he wants you to show that the equation implicitly defined, same steps for the previous one. Here in 3 dimension, let's consider, this is a very nice problem. I solved one like this at the beginning of our lecture. For this ellipsoid, that's an ellipsoid. He wants you to use the implicit function theory to find the partial z, partial x, partial z, partial y, which is a generalization of the implicit function theory. So I should check that this function is equal to 0 at the point that I'm getting the values, and also the derivative with respect to z is not equal to 0 at the indicated point. So we will determine or define z as a function of x and y, as I told you at the point 2, 1, 2. So once more, all I have to do is to check the conditions. The function already exists is equal to 0, check. Partial f partial 2 is 2z. Start substituting is not equal to 0. Now I can apply what I'm telling you. To find the partial z, partial x, all I have to do is to divide. This is partial f, partial x, partial f, partial y, partial f, partial z. In order to find partial z, partial x, I will divide 2 of x divided by 2z with a negative sign. Now I have the partial derivative. And this is, if I want to find the partial derivative of z with respect to y, it's going to be exactly the same. Those are the 2 values. Let me check. This is an introduction about the directional derivative. We really did go through this. This is how to find your directed derivative for this function. So I will start all over once more, getting the gradient vector. Be sure that it is a normal vector, multiplying them together since the function is differential. So once more, that's my function. Okay, it's an exponential sign polynomial, smooth, so it is containing its differentiable functions. Now I can use the formulas that I'm telling you about, that the directed derivative in the direction of f is equal to the gradient of f times the normal vector. So at 1 and the y over 2 and 0, I'm substituting. This is the first check. Check that partial f partial z at the point, okay, which already exists. Now I can find the value of partial f partial z. This is negative partial f partial x, partial f partial z, and this is the first implicit functions. Then the part that I've explained here is the second part, okay? So once more I can find the partial derivatives like the previous one, implicit functions. Now I can find simply, this is the part that I'm telling you about, how to find the directed derivative for this function at the indicated point using u. So all I have to do is to use this formula since it is a differentiable function, zx times 1 over root 2, zy times negative 1 over root 2. I have zx and zy from the previous part. Now I can find the values, very, very simple. Applying the values of zx and zy and making direct substitution, you will get your result. So in this problem, it's a combination between the implicit function, finding the derivatives, the partial derivatives, getting the gradient vector, then multiplying by the unit vector, as you can see. This is summarizing for the extremum point. This is the part that you came in, okay? And also I have some problems on it. I have plenty of problems. I've tried to solve them, but I think we are done for this because you really came. This is the main function. This is differentiating with respect to y, putting them equal to 0 in order to get critical points, getting the Hessian matrix, evaluating d. It is greater than 4, greater than 0, and f of x double 0. So from this, it represents a local minimum. I guess you have more than one problem dealing with all of this. The only thing that I want you to focus on is solving these equations, because those are nonlinear equations. So once you try to solve them, you will use the substitution method, substituting from one into another. And there is no direct steps to go through it. So each problem had its privacy in trying to solve this equation. I've already tried to solve that equation. The critical point is 0 and 0. I will go to the second derivative, just following the rules that we have. If double x, d, as you can see, is equal to 0, which means the test is inclusive. Try nearby point 0, 1, 0, 0, 0, 1, 1, and 0. As you can see, function increases around 0 and 0, so it's a local minimum at the origin. So once the test is inclusive, there is another methods that we will go through. This is another problem, similar treatment by the Bayesian matrix. F of double x get d, d is -1, so it's a saddle point. Another problem with the same issue, trying to solve for solving these points. This is never 0, the exponential function, never 0. That's never 0, which leads to x equal to 0, y equal to 0, so the critical point is 0 and 0. Trying to get the second derivative. The Bayesian matrix, it's exactly the same. Also, d is less than 0, so it's a saddle point. These are also some way. I will stop at this slide, and in this slide, we will go to the scheme of global maximum or global minimum. I will leave it with next lecture, inshallah. Once more to conclude this lecture. We already did go through, number 1, the implicit function theory in R2 and in R3. The step number 2 that we covered is the directional derivative in the direction of certain vector. Number 3, okay, the plane equation, which is a tangent to a certain surface in which we get the gradient vector and then multiply by the point as you saw. And the final thing is the extremum analysis, getting the first partial derivatives, number 2 putting them equal to 0, get critical point, get the Bayesian matrix, making those substitution, follow the rule. Okay, I will continue next time, inshallah. Thank you very much.